Um, Hello everyone. So this is the title of our thesis. We are dealing with service function chain placement orchestration at the edge. These are the key points I'll be covering for this presentation. So let me start by talking about what is mobile edge computing and why using this technology. So mobile edge computing is proposed as an extension of cloud computing to address the low computational limits of our local devices, such as mobile phone and laptops, so that they can service more high demanding applications such as augmented reality or 3D gaming. So in MAC, the resources are distributed to the edge server so that the user don't can so that closer within the range of radio access network. It allows user to work with services deployed closer to them to avoid direct communication straight with the cloud. In this way, it provides proximity to the resources, low latency, and location awareness. Now, there are some challenges in MEC. The amount of available resources at edge is limited compared to that of a cloud. So it is very necessary to locate those resources efficiently to handle the user's ever-changing demand. It is also very important to dynamically manage user services during the mobility in the edge. So one of the solutions here is to use this architecture called network function virtualization. So in NFV, network services are implemented as softwareized modules called virtual network function. VNFs can be dynamically deployed, scaled, and chained together to provide a variety of services to the user. It is well suited to mobile edge computing where the user freely roam at the edge because VNFs are easier to migrate. However, one of the main challenges in NFV is the orchestration of service function chain, and which has been extensively studied by a lot of researchers and is also the focus of this paper. Now, let me explain this. Service function chain is defined to be another sequence of VNFs that the user's traffic has to go through in order to implement his specific services. And the orchestration of service function chain is a problem of placing, routing, and migrating those VNFs in order to minimize users' perceived end-to-end delay with an acceptable operational cost. So now let's look at this figure right here. It shows an example of how service function chain was placed. So orchestrator here aims to find the physical resources that have enough capacity to deploy the virtual resources, which is the VNFs, and that suits users' desired services while maintaining the routing order of the virtual in the physical network, the same as a virtual service function chain. So in order to address this challenge, this problem, we design a user-managed, we decided to address the challenge by designing a user-managed service function orchestration algorithm at the edge that minimizes the user's perceived end-to-end delay. And these are the key considerations in this work. So we assume that system information is unknown. So the user has to learn about it. So this will be a user-managed and also online learning algorithm. This is also chain placement problem. We in this algorithm, we're also considering users' dynamic service demands, users' mobility, and the VNF migration cost. Now let's talk about the formulation of this problem, which includes the system model and the formulation of the optimization problem. So in our system model, we adopted a time slotting model, which each time slot represented a location phase, resource allocation phase with the duration of theta seconds. And in our network model for the computing nodes, we have a remote cloud and a set of edge servers. Each of them has capacity, and the remote cloud usually have much more capacity than the edge servers. We also assume there's a backbone network. In this network, there's routers and links. On each link, there are bandwidth and propagation delay. And for the service model, we use a set of services to denote the list of users requested services, and the traffic rate goes to each service will be scaled by a factor of alpha is I. We also use a migration delay rho to denote the time that the user has to wait before he can migrate a service I from node A to B. And now let's look at the formulation of this optimization problem. We use two binary decision variables, X and Y, to denote the decision of choosing a certain link to place a certain node, place a certain service, and a certain link to route a service from a certain service, to route the traffic from a certain service. We also use delta plus and minus to denote the incoming outgoing links from a certain node or router. And for the constraint, we formulated the placement constraint so that only one service can be placed at one node, and each service will be placed at a certain node. We also formulate the routing constraint so that single path routing is used for routing the traffic from a service, and that the bandwidth of a link should be insufficient to route the traffic from that service. And the figure right here shows a difference of the routing constraint between a certain route on a certain router or on a certain computing node. So this is our objective for this optimization problem, which includes 4 different delays: processing delay of the nodes, transmission delay and propagation delay of the links on the service function chain, and the migration delay of migrating the services on the service function chain. We also add a scale factor on each of the delay to indicate the importance of the different components in our objective. And this is a complete formulation of this optimization problem. We solve this and using a standard solver and use the result to compare with our proposed online learning algorithm as an offline performance benchmark. So this is the binary integer linear programming, which is NP-hard. And now let's look at our proposed online learning algorithm, which use the contextual bandit formulation and the CUCV algorithm. So let me start by talking about what is multi-unbanded. So multi-unbanded is a type of learning where the user interacts with the environment and gets feedback from selecting arms and get better decisions based on the feedback he received. And in this system, we have the unknown information, which we call a context, and unknown environment with the arms, which in our case is the network delays. In our work, we're trying to build a connection between the known information and unknown information with the arm estimates, which is the delay estimates. So this is how we formulate our problem, our system. So we use a system parameter theta to denote the unknown information of the system, which includes the computing capacity of the nodes, the bandwidth and propagation delay of the links, and the migration delay of every 2 node and a service. And for the contextual feature, which is the information we know, we add it to each of the option, each of the arms in order to calculate a delay from that arm. So we have the decision vector of the node and the traffic rate was sent to the node, and also the decision vector of the links and the traffic rate. So to calculate the computing delay and transmission delay, and also the propagation delay. And we also have the decision vector of migrating a service from a node that we are running in the last time slot to a node that we run in this time slot to calculate the migration delay of a certain service. And that's how we formulate our system in order to calculate the delays. And we consider, for the arms, we consider each link and node to be an option that can be selected to place a router service. And the delay of each of the arms can be calculated by multiplying the transpose of the system parameter with the contextual feature. And in a real system, there's usually a noise. We add that to the value, and to optimize, the objective is to minimize the expected cumulative delay. So this is our proposed algorithm. Change stands for chain orchestrator at the edge. So this algorithm is mainly based on the contextual upper confidence bound algorithm that is proposed in this work. So the algorithm started by initializing these 2 vectors, V and B, and it uses 2 vectors to construct an initial system parameter, and then use the system parameter and the contextual feature using the formula we mentioned in the last slides to estimate the delays, the arms with a lower bound, and then use those estimates to compute an optimal service function chain placement using this place algorithm, and then using the result that's returned from this placement to update these two helper vector V and B, and then use them to construct a system parameter again. We keep updating the system parameter until we get better and better performances. So now let's take a closer look at this place algorithm. So in this algorithm, we're giving the estimate of each option and the required services. How should the placement be done? So we use a dynamic programming by defining a cost of a placement solution recursively, and we place one single service at a time and successfully move to the next services while taking the previous solutions into account. And then in the end, we extract the solution with a minimum cost. So with this approach, we're able to get the service function placement solution, the optimal solutions, so that all we need to do is to make sure the estimates of the arms are getting more accurate over time. Now let's look at the evaluation of this proposed algorithm, which includes both numerical simulation and MINET Wi-Fi experiment. In our numerical simulation, we use Python to generate a set of nodes, a network topology, and we add weights to each of the nodes and the links to indicate the computing delay and delays. We also compare algorithm with these 5 performance benchmark serving on the cloud and edge only, 2 greedy bandit algorithm, and the offline optimum that we saw from before. So in the first experiment, we analyze the convergence performance of our algorithm, and as you can see, that algorithm is getting a decreasing average cost over the time, and is gradually converging to a fixed value that is very close to the offline optimum, around 2000 time slots, and the regret is also converging around similar time slots. So this shows the algorithm is able to learn about the system, is able to learn the system dynamics and make better near optimal decisions over time. Now let's look at the impact of the network delays. So in this experiment, we compare algorithm with these 2 edge and cloud owning algorithm and increase the level of the network delays in the system. And as you can see that our algorithm has the best performance out of all 3 algorithms. It outperformed the other approaches by an average of 20% performance improvement. And also that you can see, this shows that all algorithms are able to jointly utilize both the resources on the cloud and the edge, and also can see the different components of the objective, different delays of the objective. And the next experiment we did is to analyze the scalability of our algorithm. We first ran our algorithm for about 1000 time slot and increase the number of services and number of nodes. And as you can see that the running time of our algorithm is mainly influenced by the number of nodes than the number of services, which is expected from the algorithm complexity of the dynamic programming. And the next experiment we did is to compare the scalability with the other 2 greedy bandit algorithm, in which we increase the number of services and nodes and compare the performance, which is the average cost of the algorithm. And you can see the algorithm has the best performance out of all 3 algorithms, and is much less affected by the complexity of the problem compared to the other 2 greedy bandit algorithm. This shows the algorithm has the best scalability compared to the 2 other algorithms. So now let's look at the experience we did in MINET Wi-Fi. So MINET Wi-Fi allows us to simulate virtual hosts and virtual links, and also virtual access point and moving stations, so that we can use those to simulate a mobile edge computing network with a moving mobile user. And those are the parameters we use for these types of experiments. And also in MINET Wi-Fi, it supports various mobility models so that we can experiment on our algorithm. So in the first experiment, we track the average response time from which we send the network requests to the services we deploy on the virtual host and compare with the greedy bandit algorithm. And you can see that algorithm has outperformed the greedy bandit algorithm throughout all time slots, and it has a similar trend as the simulation, which is gradually converging to a fixed value. This shows the algorithm has better performance in practice as well, also a better learning performance. So in this experiment, we compare the performance of our algorithm, the average time, response time, with different mobility models. And as you can see, that algorithm has the best performance out of all three algorithms, and it also shows that the performance of the algorithms are indeed affected by the mobility models. And this last experiment we did is to analyze the impact of the parameters that would directly affect the performance of the algorithms, which are the parameters such as the number of nodes, link delays, and processing delays. So for this experiment, you can see that algorithm has the best performance, which it has less 1 to 3 seconds less response time compared to the other approaches. And you can also see that the performance, the response time is mainly influenced by the number of services and the processing delay, which is expected because this is in line with most real-world applications. So in conclusion, we know that in mobile edge computing, service function orchestration is more challenging because of limited resources at the edge and users' mobility. So we decided to address this problem by proposing a user-managed service function orchestration with the objective of an end-to-end delay optimization. And we propose a contextual bandit approach to deal with the system uncertainty. We also propose a dynamic programming method to compute the optimal service function placement of solution in polynomial time at each time slot. And in the end, we conducted extensive simulation and emulation experiments, mini Wi-Fi experiments, to validate the performance of our proposed algorithm. And these are the future directions that this work could take. So we could consider other service function strategies other than dynamic programming. We could also consider more complex network topologies that is more realistic, and also more complex service model that is not the single chain model that we use in this work. We could also consider multiple users, because currently we consider only one user, and maybe you incorporate different users information in the orchestrator. These are the reference that we mentioned before that propose the contextual upper confidence algorithm. And that concludes my presentation. Thank you so much.